MRI stands for nuclear resonance imaging, or known as the nuclear magnetic resonance, or NMR. MRI is invented by Paul Lauterbur in September of 1971. Paul Lauterbur and Sir Peter Mansfield were awarded the 2003 Nobel Prize in Physiology or Medicine for their discovery of MRI. The first clinical images are obtained in 1977 by Paul Lauterbur, Peter Mansfield, and Raymond Damadian. MRI uses a magnetic field and radio waves rather than ionizing radiation used in X-ray and CT to create detailed images of organs and tissues within the body. It employs RF pulse ranging from 1 to 8 megahertz. The magnetic field strength of MRI machine is measured in Tesla. So the majority of MRI systems in clinical practice are 1.5 or 3 Tesla. So this produce an extremely strong magnetic field, or up to 50,000 times stronger than the Earth's magnetic field. There are types of MRI scanner: the open MRI, which have low magnetic field strength and is made of permanent magnets, and the other is the closed MRI, which have high field strength and is made of superconducting magnets. The parts of MRI scanner are primary magnets, RF coil, gradient coil, computer system, and patient table. So I'll first talk about the RF coil. So RF coil is located within the magnet assembly and relatively close to the patient's body. This coil acts as an antenna for both transmitting signals and receiving signals from the tissue. There are RF coil that can be transmitting only, receiving only, or combined receiving and transmitting. MRI process used RF signal to transmit the image from the patient's body. The RF energy used is a form of non-ionizing radiation. The RF pulses that are applied to the patient's body are absorbed by the tissue and converted to heat, and a small amount of energy is emitted by the body as signals to use or signals used to produce the image. So there are three types of RF coil. First is the volume coil. Second is the surface, which produce high resolution images, but the field of view is small. And the third is the phased array coil. So next is the gradient coil. In order to image one slice of the body, we use gradient magnets. So these magnets smoothly increase the strength of the external field across the length and width of the body. The reason for doing this is because we can make the magnetic field different, and because of the angular frequency and the precession frequency, they both depend upon the strength of the magnetic field. So we can change the frequency that the protons are processing at different parts of the body. So the protons in the feet will be processing in slightly different frequency to those towards the chest. So if we can target a particular slice of the body by putting a specific frequency, that that slice is processing. So we can make those particular protons resonate and give us a signal. To acquire MRI images, there are 5 simple steps. First is the patient is placed in the magnet. Second is the radio wave is sent. Third is the radio waves are turned off. Fourth is the patient emits signal, and lastly, the emitted signal from the patient is used for reconstruction of the images. So to further explain it, I will illustrate the process. So as we know that our body is composed of more than 70 to 80% of water, or as we call it H2O, which consists of 2 hydrogen atoms and 1 oxygen atom. So this hydrogen proton behave as a small magnetic dipole. MRI relies on the magnetic properties of hydrogen atoms to produce images. The hydrogen atom is composed of a single proton with no neutron. As a spinning charged particle, this produces a magnetic field called the magnetic moment. So normally, the protons are orientated randomly. So there's no overall magnetic field. When the patient is placed inside the scanner, hydrogen atoms align parallel or anti-parallel to the primary magnetic field. So this is called the longitudinal magnetization in the long axis of the magnetic field. A greater proportion of the hydrogen proton align in the direction parallel to the primary magnetic field. So these hydrogen atoms are in low energy state, and the atoms that align anti-parallel to the primary magnetic field are atoms in high energy state. So the protons spin around the long axis of the primary magnetic field. So this is called the precession. The precession rate is determined as Larmor frequency. When the protons precess together, it is known as in phase, and when protons precess separately, this is known as out of phase. So when RF coil transmit RF pulse, it results in a disturbance of proton alignment. Some low energy parallel protons flip to a high energy state, decreasing its longitudinal magnetization. And also, protons become synchronized and precess in phase. As a result, the net magnetization turns toward the transverse plane at the right angle to the primary magnetic field. So after the RF pulse is turned off, several protons flip back to their low energy state, parallel to the primary magnetic field, giving up their energy to the surroundings. This results in changes to the longitudinal relaxation, known as the T1 relaxation or spin lattice relaxation. The T1 relaxation time will vary depending on the tissue composition. For example, water molecules move rapidly and do not move into low energy state quickly, so its T1 relaxation is longer. And after the RF pulse, protons that were in phase begin to dephase in the transverse XY axis. This is known as spin-spin relaxation. So this results in a reduction in transverse magnetization. So the changing magnetic moment of net magnetic vector induces an electrical signal, and the signal is received by the RF coil, and after that the computer system receives the RF signal and it performs an analog to digital conversion. The digital signal is then sent in an image processor where a mathematical formula like Fourier transform is applied, and then the image of the MRI scan is displayed on the monitor.